So if you want to know how much oxygen's uptake during a respiration, we can use this respirometer to help us. So this respirometer consists of two chambers here, two chambers. This respirometer, you can see that consists of two tubes. One tube we call as an experimental tube. Another tube is termed as control. Okay, control tube. Okay, in each tube you can see that in each tube we put in soda limes or concentrated potassium hydroxide or sodium hydroxide. So their role here is to absorb CO2. Okay, is to absorb the CO2. So on top of these soda limes or KOH or NOH, then we put a platform here. Okay, so experimental tube we include, okay, you can put anything in. Okay, for example, small enough for you to put in, for example, invertebrates like larvae, worm, or you want to put in the green beans, okay, the beans, okay, for the germinated beans. Are you clear? Okay, then we connect to this, okay, capillary tube or capillary U tube. And in this capillary U tube, you have the manometer fluid. Okay. Now, for control tubes, I will put the equal mass. If let's say here I use 1 gram of the worm, here I will use 1 gram of the glass bead, because we do know that glass beads won't carry out respiration. Anything that won't carry out respiration. Are you clear? So glass bead. If you're rich enough, you know diamond, so put diamond in. Okay, or gold. Okay. Then we connect, in this case, make sure airtight, and then you have these screw clips and also the syringe. So what's the function of syringe? Basically, if you want to repeat the experiment again, so you just adjust the syringe, then you can actually push the level back to the origin. Okay, the manometer fluid back to origin. Okay, so what actually happened in this respirometer? The idea here is very simple. Try to imagine the organism here carry out respiration, take in oxygen. Let's say they take in 10 units of oxygen. O2 take in. So then they release, let's say they release the same number, 10 units of CO2 release. So what happened to this 10 units of CO2? When they release this 10 units of CO2, soda limes here going to absorb the CO2. So if you compare these two chambers, do you realize that the first chamber experimental tube here lack of the gas particle already? Cannot. Because whatever this organism converts, take this 10 units of O2, release 10 units of CO2. So this 10 units of CO2 will be absorbed by the soda limes. So means that there is a lack of the gas particle. So means that the pressure, okay, you can see that the pressure inside this chamber is lowered. So means that the pressure lower, here pressure normal. So means that now, initially both chamber pressure is the same, but now when you start the experiment, pressure in this control chamber is higher compared to the experimental tubes. Then you can see that this manometer fluid now move towards the tube. Are you clear? It moved towards the tubes. So we can measure the distance. Okay, use different color. So now I can measure the distance move. So this distance move actually because of what? Because of O2 consumption. Nothing to do with CO2, because whatever volume of CO2 released will be absorbed by the soda limes. Are you clear? So this is the setup. So from here, I will be able to calculate the volume of O2. So we're going to look at how we're going to calculate the volume of O2 now. Okay, so first set of experiment, we're going to do it with soda lime. With the presence of soda lime, because soda lime is going to absorb CO2. Okay. So means that in this chamber, I just draw part of it only. So we have soda lime. Okay, so you have the wire gauge here. Let's say I put in my green bean, germinated one. Okay, Then I connect it to the YouTube here. Okay, so make sure it's connected tightly. So this one, I mean, I didn't, okay, okay, I draw this part also lah for the first one. Okay, so same volumes of the soda lines. Okay, but now I put in my glass bead that have the same mass with my beads. Okay, so connect. Okay, now look at this. Initially, this is the origin. So inside here, we have the manometer fluid. Okay, so when I start the experiment, because respiration takes place, when the respiration takes place, so it means that O2 is consumed, CO2 is released. But no matter how, this CO2 will be absorbed by soda lime. It imagines, huh? Okay, so I take in 10 units. Let's say, for example, in this 1 minute, I ask you take in one, you inhale in one, I mean, times, and then exhale 1 time. So this bin do the same. Inhale 1 time, exhale 1 time. But exhale out CO2, this CO2 will be absorbed by soda lime. So you can see that this manometer fluid going to move a distance. So this distance I call as X. Okay, this distance I call X. Okay, so how I measure? Because I know that this X is the distance moved by the manometer fluid due to O2 use or consumption. Clear or not? Are you clear? So I take it, let's say for example, 10 units. Okay, imagine, guys, I'll show you guys something here. Look at my pointer. Okay, so means that I start. Okay, if I allow only 1 time, you inhale 1 time, exhale 1 time. So in here, let's say for example, I inhale 10 unit of O2, release 10 units. So I inhale 10 unit O2, take in. But the problem is when they exhale out the CO2 10 units, will I change the distance here? No, because whatever release will be absorbed by the soda lime. So means stay here. Now try to imagine, if let's say I take in 10, release 20, doesn't matter. I take in 10, whatever release will be absorbed by the soda limes. So means that if I know the diameter of the tube, we wouldn't be able to measure the radius. We only can measure diameter. Okay, so if I know the diameter of the tubes, D stands for diameter of the lumens of the capillary tube, then I can calculate the volume now. Volumes of O2 used or consumed will equal to pi d over 2 square multiplied with the distance. That is the volumes of O2, okay, used by the organism, okay? And then I can calculate the rate of respiration now. The rate of respiration, which I define equal to the rate of O2 consumptions, okay, will equal to the volume of O2 use per unit time. So depend on your time. In this case, in 1 hour, for example, or in 10 minutes, for example. Are you clear? Okay, so the rate of respiration now I can calculate by using this respirometer. So why? Because I already get the volume of O2 used already. So the volume of O2 used here equal to pi d over 2 square multiplied with the x. And x stand for what? The distance okay, moved by the manometer fluids due to the O2 consumptions. Are you clear? Okay, so stop for a while. So now look at this. In order to calculate R cube, so first volume O2 we solve already the problem, but how about volume of CO2 release? Because volume of CO2, whenever CO2 release, CO2 will be absorbed by the soda lines. Are you clear? Okay, so now what we're going to do here is we have to do a modification, because we do know that, okay, as long as soda lime is there, we can't get to measure the volume of CO2. So we remove the soda lime. But when you remove the soda limes, then we must come up with an assumption here. What is the assumptions? So first, the rate of respiration remain constant. So means that with or without soda lime won't change how much volume of O2 taken in by the organism. Are you clear? So means that in the first experiment here, if I take in 10 units of O2, if I repeat the experiment, let's say 10 units O2 per minute, then if I repeat the experiment here later without the soda limes, then the rate of respiration is still the same, means still take in 10 units of O2. This is the assumption. To make this assumption more valid, so one of the key points here, that very important here, you have to make sure that use back the same organism. You don't change, because each individual organism, they have different rates of the respiration. Cannot you and me, even though both of us are humans, but we breathe in and breathe out differently. Are you clear? So therefore, to make sure that the rate of respiration remain constant, then we have to make sure that we use back the same organism and remove the soda lime. So once you remove the soda limes, we're going to have 3 outcomes here. Okay, 3 expected results. So we're going to discuss each of them. Okay, so look at the first outcome without soda lime now, yeah? We try to imagine, we remove the soda lime, replace the soda lime with other things, okay? Glass bit, for example. So first outcome, I only draw the U-tubes here. The capillary U-tube. So this is the origin. Okay? So what is you observe? What you observe here, observations after particular times already, observations. Okay, no change in distance. So means that starting point, this is a manometer fluids. Okay, at the end, also the same. There's no change in the manometer fluid. So with assumptions that, okay, before the start experiment is after. So what actually happened here? What actually happened? So in this case, now we have to understand. We do have the assumption. What assumption? They take in the same volume of O2. So means that because now the plants or these beans, okay, release the CO2, but CO2 cannot be absorbed, right? No soda lime. So means that they take in this volume of O2. So if imagines that we don't change the tube, don't change the organism, so they take in O2, cannot. That's why manometer fluid move up. Release CO2. Cannot. So this distance still X. Are you clear? So what is the volume? Okay, not volume. So we know that X is equal to the distance moved by the manometer fluid due to O2 consumptions. But at this moment, can you see that? I take in this volume of O2, release the same volume of CO2. Cannot. Okay, so therefore, in this case, X also represents the distance moved by the manometer fluid due to CO2 release. Okay, so we will calculate volume of CO2. Volume of CO2 equal to pi diameter over 2 square multiplied with X. So if you calculate the RQ value, volume of CO2 release over volume of O2, then you get pi d over 2 square X divided by pi d over 2 square X. Okay, clear or not? And if as long as the diameter they are the same, so means that actually pi and pi can cancel out the effect, diameter can cancel out the effect, so X over X so equal to 1. Can you see that? So what's RQ value? RQ value equal to 1. So what you can interpret here, aerobic respiration. Okay, and respiratory substrate is carbohydrate because RQ value equal to 1. So first outcome. Okay, so this is the second possible outcome. Okay, second possible outcome. So in this second possible outcome, you can see that, okay, that is a movement already. That is a movement. So this movement, if I measure the distance, is y. Okay, y. But this y, if you compare, if you assume, our assumption saying that the rate of the respiration remain constant. So if the rate of respiration remain constant, means what? Means that we always have to include this, the X. Cannot. Means that take in. So what's the X here? So X means take in the amount of the O2. So means that try to imagine the bin take in O2. Release CO2. Oh, stop already. If it release more, it will push it more, right? But now it release. Imagine, look at my mouse, okay, my cursor. Take in O2. Release CO2. So this is the part actually contain CO2. Can you see that? Are you clear? So if I want to find out the distance moved by the manometer fluid, okay, due to CO2 release, calculations here will equal to what? X minus Y. Correct or not? The distance. Understand? Look at my mouse again. Initially, I take in O2, release CO2. Can you see that? So this is the part where CO2 release. The distance moved by the manometer fluid due to the CO2 release actually is X minus Y. Are you clear? X minus Y. So what is RQ value? So RQ value equal to CO2 release, X minus Y, divided by the volume is X. But I don't multiply with pi because pi d over 2 square, both of them are same. So if you look at these guys, the RQ value definitely less than 1. Hey, what I'm doing? Less than 1. Are you clear? RQ value definitely less than 1 already. Okay, very simple. What we calculate is X over X minus Y over X. Can you see that? So X over X equal to 1. This one minus something. 1 minus something confirm less than 1. Correct or not? Okay. Mathematics. So RQ value less than 1. So what is the conclusion? Conclusion is aerobic, still aerobic respiration. But what is the respiratory substrate? Then we look at the value. If let's say RQ value equal to 0.7, then it's lipids. If RQ value that equal to 0.9, then we know it's protein or mixture. Are you clear? If let's say 0.8. Clear? Okay. Okay, so this is the third outcome, a possible outcome for the third ones. Okay, so with the assumptions, the bean still living, the organism still living, so they take in the same volume of O2. So it means that you still have the X here. Correct. So if you look at and you follow my pointer here, so I take in O2. I release CO2. Get it? Can I see? Okay, origin. So I start the time, take in O2. Cannot release CO2. So means that this is the part where contributed by CO2. Correct or not? Right. Okay. So means that if I want to know the distance moved by the manometer fluid, due to CO2 release will equal to X plus Z. Correct or not? Right, equal to X plus Z. Follow my mouse again. I take in the O2, release CO2. Right, so means that in this case, I can calculate my RQ value now. So RQ value equal to volume of CO2 released, but I don't calculate the volumes, but I use the distance, X plus Z divided by X. So means the RQ value definitely more than 1. So your RQ value more than 1, therefore anaerobic respiration. Okay. So we have this organism was placed in respirometer with the soda lines for 10 minutes. Distance moved by the manometer fluid is found to be X millimeter. So soda line, we remove it. So the same organism will place it back because assumption, okay? We assume that the rate of respiration remains the same, okay? So complete table 5.8 to show the distance moved by manometer fluid due to CO2 release. Hence, we state the RQ value. Okay, so first, so if let's say there's no change, it will measure, okay, 0 mm. Why? Because no change. Why is no change? Because it take in X units of O2, release X units of CO2. So the distance actually equal to X. So the RQ, okay, will equal to X divided by X. So RQ equal to 1. Okay, now you state it. Okay, equal to 1. So what is the conclusion? If equal to 1, aerobic respirations, and the respiratory substrate is carbohydrate. Don't say glucose, not necessarily glucose, it can be others. Okay, so we say carbohydrates. Okay, unless question tell you, okay, it's glucose, then you say glucose. If no, then we put it as general carbohydrate. Lower than X, higher than the initial position. So we measure is Y. So in this case, the distance actually is X minus Y. So RQ value less than 1. Okay, RQ value less than 1. Okay, so less than 1 basically means still aerobic respiration, but respiratory substrates can be lipids or proteins. Okay. So if the level of the manometer fluid is lower than X and also the initial positions, are you clear? So in this case, Z. So we take in X unit, release X plus Z. So in this case, due to CO2, X plus Z, so RQ value more than 1. Okay, so when RQ value more than 1 means aerobic, it's an anaerobic respirations. Okay, so with this, do you guys have any other question you guys want to ask? If no, we have done for today's class. Okay.